All right, this is a video for the second half of Unit 15, Day 5. So hopefully you have two sheets in front of you. The first one should be a warm-up. It's called Practice with Z-Scores. And the second sheet that you need is the notes from yesterday. So we did the first 2 pages yesterday. We're going to be starting on page 3. But first, the warm-up. So this is kind of going back a little bit, practice with Z-Scores. 2 versions of a standardized test are given, an April version and a May version. The statistics for the April version show a mean score of 480 and a standard deviation of 24. The statistics for the May version show a mean score of 510 and a standard deviation of 20. Assume the scores are normally distributed. So remember, when we do normally distributed, I'm always allowed to use that bell curve. Okay, first question. Claire took the April version and scored in the interval 510 to 540. What is the probability to the nearest 10,000th that a test paper selected at random from the April version scored in the same interval? Okay, so here's what I'm looking for. We know it's normally distributed, so that's how I know it's not an old probability question. It's using the normal curve. What always goes in the center of the normal curve? The mean. And make sure we're doing the April version. So the April mean is 480. So we're going to put 480 right here. And she scored in the interval 510 to 540. So we're basically looking at what's the probability I score between 510, which should be right about here, and 540, which is right about there. And I'm looking for that probability. Okay, so if I want that proportion, you know, we can go right to our calculator and do normal CDF. My lower would be 510. My upper would be 540. The mean we're using is 480. And the April standard deviation is 24. Okay, so show me that work, show me the picture. Then we go to our calculator. Remember where normal CDF is, second bars, choice 2. Lower is 510, upper is 540, mean of 480, and standard deviation of 24. Gets us 0.09944, etc. And wanted the probability to the nearest 10,000th, which again is 4 decimal places. So that's about 0.0994. So only about a 10% chance that people scored in that range. Okay, so that we didn't need z-scores with because our calculator could do the z-scores themselves. But for part 2, or the second question here, it says Holly took the May version. In which interval must Holly score to claim she scored as well as Claire? So the hint there is that we need the same z-scores. So we got to find what each of their z-scores are and make them the same. So first, let's find what Claire's z-scores would have been. Okay, so remember how to find a z-score. It's observed minus the mean over the standard deviation. So Claire's lower value is 510. So 510 minus the mean of 480 divided by the standard deviation, which was 24, I believe. And we come and type that into our calculator. 510 minus 480, enter, divide by 24, and her first z-score is 1.25. And the upper range of her z-score, which was 540, minus 480, divided by 24. So 540 minus mean of 480 divided by 24 is 2.5. So those are Claire's z-scores. We need Holly's z-scores to be the same. So remember what z-scores actually do is they're relating it to the parent normal curve with a mean of 0 and a standard deviation of 1. So z-scores let us compare two different data sets and kind of put them on a level playing field. So if I use the z-score to see how many standard deviations Claire was away, she was between 1.25 standard deviations above and 2.5 standard deviations above. We need Holly to be the same amount away, even though she took a different test. So just because someone might have scored in a different range doesn't necessarily mean that they did better or worse. It all comes down to how it relates to the z-scores. Okay, so we need Holly's first z-score to be 1.25. What we don't know is what her actual score on the test was, so we don't know the observed value, so we're going to call that x. Minus Holly's mean, and since Holly took the May version, that had a mean of 510 with a standard deviation of 20. So we have to do x minus 510 over 20. And to solve for that, we'd multiply both sides by 20. Okay, so I got to do 1.25 times 20. Gets me 25. So 25 equals x minus 510. And when I solve for x, add that 510 over, we get that her lower score has to be 535. And we need her second z-score to be the same as Claire's second z-score, 2.5. Similarly, x minus 510 over 20. So if I multiply by 20 there, multiply by 20 there, 2.5 times 20, you might be able to do that in your head, but it's going to be 50. So 50 equals x minus 510. And getting x alone, add the 510 over, we get 560. So that tells us that Holly must score between 535 and 560. So Claire's score of 510 to 540 is equivalent to Holly's score being 535 to 560 on her SAT. So if Holly claims that she did better just because she got a 560, Claire can come back and say, well, no, your test was easier, so that's why you had to score higher to be as good as I was. And that's what z-scores are useful for. Okay, so now let's get back into the sampling distribution stuff. So we were on page 3, and this is where kind of the interesting part really happens. Yesterday we talked about p-hat, and we talked about selecting random samples and how we could randomly select based off of a random number generator. But today we're going to talk about simulations, and simulations kind of give us a way to represent a situation that would be hard to do in real life, but would have similar characteristics. So here's an example. We're going to be creating a sampling distribution of sample proportions. And suppose I have a candy machine that dispenses Reese's Pieces, which come in orange, yellow, and brown. The machine holds 10,000 candies. Every time you put in a quarter, the machine spits out 25 candies. Suppose for each group of 25 candies, you want to see what proportion of the candies where the machine spits out are orange. So it starts by saying about which proportion or what proportion of the 25 candies would you expect to be orange? Okay, well, let's think about it for a second. If they come in orange, yellow, and brown, I would think that the company would make an equal amount of all of them and just put them all in the bag or all in the candy machine. So out of 25 candies, what proportion would I expect to be orange? I would say about 33%. Because if they're all equal and there's only 3 of them, there should be an equal number of each. Okay. Number 2, will you always get the same proportion of orange candies each time you put in a quarter? No. I'm not going to get exactly 33% every time I put in a quarter. Maybe there's a bunch of yellows on the bottom and I get a ton of yellows and only a couple of orange. Or maybe all the oranges fell to the bottom and I have a bunch of oranges. I'm not going to get exactly 33 every single time, but I would think it should be relatively close. And that's the problem with statistics. When I say relatively close, how close? Well, I don't know, 36% is relatively close. Is 38%? Yeah, it's getting a little bit bigger. 50%. If I get 50% orange, that's kind of weird. That's not really 33%. So relatively close means within the ballpark, but again, it's a little iffy. Okay, so to simulate this situation, I'm going to use an online program, and we're going to use this exact scenario. So suppose we put a quarter in the machine 4 separate times. Remember, each time it spits out 25 candies. We're going to record our results from each trial by putting a dot on this graph. So I'll show you what I mean. So if I go to this website, it lets me put in what probability I want orange to be. So if I really think there's an even number of each, I'm going to put 33%. So there should be about 33% orange. Every time I put a quarter in, I'm going to get out 25 candies. And I'm just going to do this one time. So each time I press draw samples here, it's going to represent me putting in a quarter one time. Okay, so here I go. I'm going to look at the proportion of orange. I want to know what percentage are orange. And here I go. So I put in my quarter, look at it spitting it out. It's counting the oranges. It's counting the non-oranges over here. Okay, so here, even if the true probability is a 33% chance I get orange, look at how many orange I got this time. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 out of 25 is 44%. So that's pretty high, even though there's really only 33% orange in here, because that's what the program is based off of. And then notice what happened down here. They put a dot right between 40 and 48. That represents that that sample had 44% orange. Okay, so on my notes here, get rid of that. On my notes, that first trial was 0.44. So I have to go to 0.44 and I put a dot. So that trial represents that one time I did this, I got 44% orange. Okay, let's do this again. So I'm going to do another sample. Here we go. Counting the oranges. This time I get less, it looks like. This time I got 32% orange. And that's more in line with what the actual probability of orange is. And notice a dot popped up on this graph down here at 32%. Okay, so let's record that. So all of these trials are my p-hat values. Remember, p-hat is just one sample proportion. And we put a dot at 32%. Okay, let's do a couple more. Here's number 3. Counting out the oranges, there they go. Look, I got the exact same thing as last time. I got 32%. So what happens on the chart? Oh, there's a dot right above the old 32%. I'm essentially going to be drawing a bar graph. So the more dots in one spot, the more times that occurred. So trial 3 was also 32, which isn't super abnormal because it's right around 33%. And there's my dot. And let's just do one more time. There it goes, counts them up. And this time, look, what do you know? 32% again. Okay, so this is only 4 trials, and I got 32% 3 times. Not every time. Like there was that time I got a weird situation where I got a lot more oranges than before. That can happen. So clearly I don't get the same amount every single time, but I should normally expect it to be around that mean. So what do you think this graph would look like if I did it 100 times? Or if I did it 1,000 times? And we're going to look at that in a second. Okay, so what we're drawing, this graph here, is called a sampling distribution. Of sample proportions. So each p-hat is a sample proportion. It's how many oranges I got in one sample. All of the p-hats together on this graph is called a sampling distribution because I can see in a lot of trials where these p-hat values fall, how they're distributed. So sampling distribution of sampling proportions. Okay, so back to the question I asked a second ago. If we do a large number of trials and get a large number of p-hat values, the graph will become approximately normal. So that's where it connects to what we did earlier this unit. we would expect most of these dots to be right around the center of 0.32 or close to it. So you can kind of envision a normal curve happening here, and there'd be some weird outliers like that 0.44 on the very end that happen once in a while, but usually it's going to be clumped around the middle, which is a normal curve. Okay, the mean of the sampling distribution of sample proportion, so the mean of all the p-hats, should be approximately equal to the true mean of the entire population of Reese's Pieces. We told the computer that the actual population was 0.33. If I do this a bunch of times, the average of this sampling of average of all these dots should land right around that center value of 0.32 or 0.33. So it makes sense that the mean of this sampling distribution should be equal to the mean of the actual number of Reese's Pieces. So how can we use this? Well, actually, before I'm getting into that, let's kind of talk about what I just showed you. So I'm going to reset this. Let's look at 100 samples. And it's still going to show you doing one of them, but it's doing it 100 times. And there's all the dots. What does it look like? It looks like a normal curve. And if I click Summary Stats, look at that. The mean of all of these dots is 0.431. Standard deviation of 0.1. But that mean is really close to our actual mean of 0.33. Now, again, it helps to really understand what you're looking at. How are they calculating this mean? They're taking every one of these dots, so 0.08 plus, what's that, 0.12 plus 0.12 plus 0.16 plus 0.16. They're adding every single value of these dots, dividing by 100, because there's 100 dots, and they get the mean. So the average of all the dot values, the average of all the p-hats is 0.34, right near the middle of this graph, which is approximately equal to the probability of orange candies. Okay, well, what's going to happen if I do 1,000? Let's see. Okay, now the mean's 0.332. It's even closer to the actual probability. And the standard deviation's a little bit smaller. It was 0.1 before, and now it's 0.092. And if you look at the curve, it looks even more like a perfect bell curve. So the more samples we do, the more those outliers won't affect it so much because we'll get more and more of those middle values. So the more number of samples, the less variability, meaning the lower the standard deviation, and the better value the mean is, the closer the mean actually is to the true population mean. Okay, makes sense? Of course it does. Okay, excuse me. So how can we use this to help us? Well, in the program I just did, we looked exactly at if it really was 0.33. Let's say I didn't know what the true population mean was, and I wanted to use a sampling distribution to tell me. Here's example 3. I have a theory that the true proportion of orange candies in my candy machine is not 33%. To test this theory, I do 100 trials, each of size 25, and record the proportion of orange candy in each of my samples. The resulting sampling distribution of sample proportions is shown below. So this is, rather than me doing it with the computer, let's say I actually do this in the store somewhere. I get so many orange candies every time, I don't believe that there's 33% orange. So I do this 100 times, track my results, and this is what I get. It says, based on the sampling distribution, do you think the proportion of orange candies in the machine really is 33%? Why or why not? Okay, well, I could take the mean of all these dots and see what the actual average is, but just by looking at the sampling distribution, would you say the mean is 33%? Do you think the mean's over here? Well, no, there's not many dots on this side. I would say the mean is probably somewhere in this range. This is where most of the dots are. This is where the middle of the distribution is. I'd say the mean is closer to 0.48, not 0.33. So no, I don't think it's actually 0.33. I would say no, the mean of distribution appears to be closer to 48%. Closer to 48% than 33%. So again, statistics is iffy. Does that mean the true population proportion of orange candies isn't 33? Not necessarily, but I've got some evidence to suggest that it looks like maybe not. It looks maybe that there's a lot more orange candies than the other ones. Okay, part B says, suppose I put a quarter in and only get 4 orange candies. Would you consider this to be abnormal? So 4 orange candies is 4 out of 25. What is 4 out of 25? Let's check it. 4 out of 25 is 16%. Is getting 16% orange abnormal? Let's look at our sampling distribution. I did get 16% a couple times, but only 2. So 2 times out of 100, I got 16%. That's pretty abnormal. It's a 2% chance. So I'd say, would you consider this to be abnormal? Yes. This occurred only 2 times out of 100. Or about 2%. So what does the Regents consider abnormal? Generally, they're going to try to make something under 5% if it's abnormal. So 2% is definitely abnormal. And they're not usually going to be dancing around 5. They're going to be either definitely below 5 or definitely way above 5%. So we're going to say for our purposes, abnormal is about under 5%. Okay. So that's how we can use these sampling distributions to kind of test theories. Let's look at the next page. Student flipped a coin 100 times, calculated the proportion of heads, and repeated this process a total of 40 times. Below is the sampling distribution of sample proportions of heads. The mean and standard deviation of the sampling distribution is 0.405 and 0.046. Do you think this was a fair coin? Why or why not? Well, what do you think? If this is the results I got, was the coin I flipped a fair coin? What's a fair coin mean? Well, in a fair coin, what's the probability that you get heads? It's 50-50, so 50%, 0.50. Did I ever get heads 50% of the time? Sure, there's a bunch of dots over here. But the mean of the sampling distribution is more like 40, 41%. So if the mean of the sampling distribution is supposed to equal the true population mean, doesn't equal. So I would say this is not fair. X bar equals 0.50 in a fair coin. And this is only about 0.405. So I would say probability that heads is 0.50 for this coin is unlikely. And before I move on, let's make sure you understand what you're looking at here. A student flipped a coin 100 times. This doesn't look like 100 dots. Calculated the proportion of heads and repeated this process 40 times. That's the number of dots. So each dot represents flipping a coin 100 times. So that's 100 coin flips, that's 100 coin flips, that's 100 coin flips, that's 100 coin flips, and they're taking the proportion of the heads every time. So they only did this trial 40 times, but each individual trial is 100 coin flips. That's what they're showing you. And they're showing you the average proportion of heads out of those 100. So if I got 40 out of 100, then I'd have a dot right at 0.40. If I got 50 out of 100, I'd have a dot at 0.50. That's what I'm looking at. Okay, so we've done a lot with sampling proportions. Let's talk a little bit about sample means. It says some statistical studies do not lend themselves to studying sample proportions as in the last scenarios. For example, suppose I wanted to determine the mean height in inches in a town of 20,000 people. Rather than gather all 20,000 people's heights, I could take several smaller random samples of people in this town, determine the mean height of those samples, and create a sampling distribution of sample means to determine the true population mean. So if I've got 20,000 people, it'd be really hard to figure out to talk to all 20,000 and ask what their height is. If I did that and averaged all of them together, I'd get the true average height of the 20,000. But what would be easier Let's say I just take 200 random people, sorry, 20 random people, and do that 200 times. And I create a sampling distribution. So let's say the first 20 people I take, I don't know, let's say I go to 20 people in this classroom right now, take all their average heights, and let's say the average comes out to be 62 inches. So the average of those specific 20 people is 62 inches. Does that mean the average of the whole town is 62 inches? No. It just means that I have one sample group whose average was 62. Okay, so now let's say I go and take another total random sample of 20. So these another 20 people out of these 20,000. And let's say those people are a little bit taller. They all have an average height of 65. So I put a dot at 65. If I do this 200 times and get 200 dots, I should expect to see a normal curve happen again. And the mean or the middle of that normal curve should probably be the mean of the actual 20,000 people. So conclusion, the mean of the sampling distribution of sample means, so I'm calling this sampling distribution of sample means because it's averages of samples as opposed to percentages of heads or something, will be approximately equal to the true population mean. And just to differentiate with notation a little bit, the sample means we've been using X bar with. If I want to talk about a population mean, that's when we use that mu. So that's the mean of the entire group. And that's similar to sample proportions. We said that the number of proportions of the sample distribution was equal to the true sample proportion. The other thing we can say is as sample size, and usually they'll use n per sample size. So as sample size n increases, the standard deviation of sample means decreases, which should make sense. As I take more samples, it should be less crazily spread out and more clumped around the middle. So that's essentially saying becomes more normally distributed. Okay, so sample means are just another statistic I look at as opposed to sample proportions, but hopefully you're seeing the ideas are exactly the same. Okay, so let's go to the last example, number 6, sorry. Several random samples of size 20 were calculated and the mean SAT scores were calculated. The plot below shows the distribution of the mean SAT scores for their samples. Okay, so again, think about what you're looking at. Each dot samples of size 20, so each dot represents 20 SAT scores. They take those 20 SAT scores, average them, put a dot there. Is this sampling distribution of sample means? Exactly, yes, it is. Why is it? Each data point or each dot represents the mean SAT score calculated from one sample of size 20. So this is a distribution, or how they're distributed, of all those different sample means. It says, what's the approximate mean of the sampling distribution of sample mean SAT scores above? How can you calculate the exact value? Well, the approximate mean would be what's right around the center. So I would say right around here is the center. So what's that? 480-ish, 478-ish, something like that. So about 478 maybe. And if I wanted to get the true actual exact value, I would take every single dot. So 420, I don't know, 425 plus 430 plus 430 plus 430 plus 440 plus 440, divide by however many dots I have, and I would calculate the exact value. So how could I calculate the exact? Could take value of each dot, divide by total number of dots, exactly how we find averages usually. So basically I'm finding the mean. What do you conclude the population mean of SAT scores actually is? Well, we got the actual average here. The average of the dots was about 478. That's supposed to be equal to the true population average. So what the average of the sampling distribution is should equal approximately the true population mean. So I would say true population mean, mu, is about 478. And that's that first box I said yes on the last page. The reason is because the mean of sampling distribution should always be approximately equal to the population mean. Now I say always, but that's a little bit misleading. Always, as long as I have a good sample, as long as I have enough dots, things like that. And then D, how would increasing the sample size from 20 to 200 affect the variability and standard deviation? So if I, instead of just taking the average of 20 in every sample, if I took the average of 200 in every sample, the dots should be way less spread out. They should be more clumped around the middle. So they should be less variable, meaning I shouldn't have as many crazy outliers, because in 200 dots, I'm less likely to get a crazy high or crazy low average. And if it's less variable, that means the standard deviation would decrease because it's less spread out. And standard deviation is a measure of how spread out something is. Okay, so this is really the heart of statistics. We got into it today. So hopefully this made sense. You understand what you're looking at. Give the homework a shot, and that's it. Good luck.